I'm upset that nobody's really replied to my offer to live stream Hearthstone ladder climb on Monday. Can you see my post about that on Slack? If anybody, I expect to see it. Because I play Hearthstone like competitively, so the season resets on Monday. So I was thinking about doing like a live streaming the ladder climb, but associate it with like computer science learning. Because I really think that, because I mean, one of the things I teach is this idea that, you know, we solve problems in terms of the tools we have available to us. So on each Hearthstone, if you haven't played Hearthstone before, it's like Magic the Gathering, it's a card game. But you know, you have the tools or what's in your hand. The problem you're solving is either I'm trying to beat the guy as a whole, but I'm either going to attack him this turn, or I'm going to clean up his minions or whatever it is. So you're constantly solving these problems and kind of talking out the possible strategies you can do. It's like chess for geeks, but I really think it's like good practice for computer programmers. So I thought, I mean, I play anyway. So the question is whether I sit in front of a computer or I do it on my iPad on the couch. But I put up there, like, I was thinking about doing like a 2 or 3 hour live stream on Monday night just to do the ladder climb. Well, I don't care about that, you know, more just like as an entertainment exercise. So I wanted to get an idea of how many people would actually watch. You know, if one person is there, maybe I wouldn't do it. But if I had like, you know, 9, 10 people who were like, hey, that sounds kind of interesting, I would maybe watch it for a bit. You know, there's like, okay, well, it's worth doing it and just to see what, you know, whether it's of interest or whatever, but I would kind of talk through it like it was a lesson, you know. So I don't know, read it. I won't be offended either way, but it really boils down to whether or not I like put clothes on and play in front of the computer or. Oh, that's the deciding factor. It's like, that's a deal breaker. You put clothes on, I'm not, no, I'm a no-show. All right. What am I doing? Okay, I already got that on. I have Keynote open, and this is 450, right? Okay, and we're almost there. Oh, let me start the recording so I don't. Oh, I did already start the recording, so we're good. We are almost there for the virtual machine thing. Mark Newhouse has created us our Wi-Fi, so this guy right here is actually the real university-provided CUWCS Wi-Fi instead of us running our own thing. The virtual machine server is working. The problem right now is the server sits inside of a router, so there's from a networking perspective, go back to this guy here. Technically, there is a router right here. And that, of course, is in white. So that means that our vCenter gets an internal IP address, like 192.168, whatever. This router is connected to the CUWCS network, and my computer, did I put that somewhere? Oh, I did have to copy something. Littman laptop is connected to CUWCS Wi-Fi, which technically is connected directly to the CUWCS network. So as of right now, this router is acting like a firewall, blocking us from getting to vCenter. So what we do is we set up something called port forwarding, so that technically I'm hitting the IP address of this router, which then forwards me to the internal IP address of vCenter. That's working. The problem right now is vCenter has some sort of like anti-attack type stuff built into it that's, I can hit it, and as soon as I try to log in, it kills the connection. So right now, this guy, we were trying to figure out its security issues. Now, alternatively, we have a couple of ideas to try, is that we can take vCenter, and instead of having it plugged into the router, we can just plug it directly into the CUWCS network and just bypass the router for it and have everything else happen inside the router. Then we'd be able to access it. So we're trying to figure out the right way to do it. We're probably a couple of hours of debugging from getting it working, but all the parts are working and stable. Right now, we just can't quite get to it. In fact, I still have Safari open here. Here, let's see if they actually maybe made any progress with it today. Doesn't look like it, but doesn't matter because we're close. So we will have that set up fine. And as of right now, that network is available everywhere on campus. It's a hidden SSID, so you can't actually see it. I don't think that is Mark Newhouse's intention, but this is the current deal. So presumably you would be able to get to your virtual machine directly from like your dorm. But like I said, worst case is if it got shut down, you just come down here, go for a walk, boot it, then you'd be able to get to it through VNC Cloud. But once that's done, hopefully by, let's say, Monday, hopefully, we'll see. Then I'll do an official demo of it, so you have a video that shows the exact steps that you would actually take to do it, as opposed to this is how it worked last week and whatever. All right, so let's go here. So last time we were talking about, so we talked about compiling, and that it requires us target two different things, right? We're targeting what operating system and what architecture. Okay, those two pieces of information are important to us. Now we're not writing compilers in here. We're writing software that runs on an operating system with an emphasis towards plugging into operating system services as opposed to like a business application. All right, so we're thinking about those underlying things that the operating system provides for us. So last time we were talking about this idea of drivers, which is like specialized software for making a piece of hardware. The example I used was the GPU. You get a fancy GPU that knows how to do 4,000 things over and above the default generic VGA capabilities that your operating system comes with. That's the software for it. So one of the things we might do is we might write drivers for an operating system. Okay, that's pretty much where we left off. Does that sound correct at this point? Okay. So let's think about that. Let's roll back in time a little bit. Am I sharing my screen? How long into the online people are going to tell me I wasn't sharing my screen? That's a 0 in today's quiz.
Well, I mean, I could kind of just listen to everything that you're saying.
Still failed.
Yeah, I didn't know there was slides at first.
I didn't know what I didn't know.
Until you were
How defensive
ready.
they're all getting now.
Thought you were just talking, you know?
That's still a 0.
I was so mesmerized by your voice, I just got carried away and forgot that.
I can appreciate that. Who wouldn't be? But it's still a 0. We'll say this again. He's just stuck on that. It could get kind of funny if I do that. If people are interested, I do that live stream. I just go on this huge losing streak. Because you start off, because I'm legend in there, which is like the world ranking level, but then every season you reset to like the lowest level and you have to climb the ladder again, but so does everybody else. So if I start bumping into other world ranked players, I'm just losing at like bronze 8 or something like it. Just I just sit there for 3 hours. And then you have like you might be losing like a 12-year-old. They got their like funny screen name. Like I just lost the fuzzy kittens. Who thought he was going to drop a T-Rex on me? It could be kind of funny. My wife hears all about it regardless, so I have an audience saying whether you guys show up or not. And I promise you, she pays up complete attention. So, although the other day I was playing a ranked game and I let her make all the moves and we won. And she doesn't know the rules at all. So what does that say about the skills that required for this? not all she was just doing it based on she liked the look of the card. It's like, that was a pretty one. Let's play that one. It's all sparkly. All right. So we talked about what these drivers are. So now, if we think about let's go back in time and think about the history of operating systems. And maybe a good example, if we roll way back, is kind of like some of these older Unix operating systems. Maybe, how many of you have heard of Sun Microsystems? They're called Oracle now. Well, Oracle existed even when Sun Microsystems existed, but then Oracle acquired Sun Microsystems. Sun Microsystems are the makers of Java, but they also were a hardware company. So they created Linux, or it wasn't Linux, it was Unix servers. So think of them as like a competitor against like Dell. They had hardware. They had their own processors called Spark chips, which was a RISC-based architecture. They had their own version of Unix called Solaris, Sun Solaris Unix, which was pretty popular in the early-ish 2000s, 2005, 6, 4. So probably somewhere in that zone is where they were still pretty popular. But you kind of go back and put yourself in the shoes of, let's say, you were kind of a network admin person, and you were maintaining a computer, you had your office machine or something like that, or you were working on one of the network machines, and you had what were called Spark stations. You had a Sun Spark station, which is like a fancy way of saying a really expensive computer that had no reason to be that expensive. Now the reality is if you were a gamer or a general purpose consumer user or something like that, you would never get a Spark station. You probably could still go on eBay and find old Sun Spark stations, and they're probably disproportionately expensive for no good reason other than just history or something like that. But even back then, they were just expensive. But the idea would be is that you would never go out and buy the latest, greatest graphics card and try to put it into that machine. It wouldn't have made sense. That's just not what those computers were used for. They were servers. Servers are workstations for like developers and things like that. Now, with that in mind, some of the early versions of Unix, let's say Solaris Unix as an example, were these giant monolithic operating systems that what they tried to do is they tried to include driver support for all of the stuff that's currently industry standard type stuff being used in the networking world. Now, you might imagine that we have probably a lot better chance of making a guess about what that stuff is than we have at making, all the different configurations for consumer computers, right? A consumer, we take any one of our laptops in here, we have different specs on the laptops. We might have a different processor, a different GPU, a different this, that, the next thing, whatever it is. So servers were a lot more standardized. So for a long time, Unix-based operating systems at the very least, and this is still true also in the earlier Windows operating systems. We kind of talked about that where Windows 98 to Windows 2000, we had made that translation over to the from the consumer to the business side, and we lost all that driver support. So right now I'm kind of talking about like that on steroids where, Solaris was never meant for like grandpa to use a Solaris Spark station type thing. So you had this operating system, and what it had is it had all of the drivers and stuff hard-coded into the operating system, which means that if you had this operating system and then you made a new piece of equipment came out, a hardware manufacturer released a new scanner or a new printer or something like that, you might not be able to use it on the operating system because the operating system didn't ship with the drivers for it. All right, so or we'd have to go down to like we talked about last time with like VGA drivers, whatever the most generic thing was, or it was a limitation on the hardware makers. Maybe the graphics cards people back then, they would have had to say, oh, well, yes, we can make something awesome, but we're just gonna make something that's VGA compatible because that's all that will work on this machine, okay? So that was kind of a challenge, and we've kind of evolved past that now, right? Now it's pretty common that, people get different classifications of hardware depending on the way they're going to use the computer and that kind of stuff. So operating systems had to evolve with that. Now, I'm going to just create another slide here real quick. I'm assuming all of you in here have at least heard of Linux, right? So Linux is an open source version of Unix. Okay. So that means you can go in, look at the Linux source code. And at some point, we'll actually do that. We'll look at the Linux source code relatively soon, actually, as we start talking about modules. But it's an open source version of Unix. And one of the cool things, modernly, for instance, I run Ubuntu Linux when I use it now because it just kind of works. And think of it as almost like the Windows or Mac OS version of Linux. You install it, everything's nice and graphical, everything kind of works, it auto detects most of your hardware. The windowing system just kind of functions, it works. You go back to some early days of Linux, a lot of times you would end up with just like kind of a DOS looking prompt, a Unix terminal prompt, because they didn't detect your graphics card, and so that way, so you couldn't start X Windows, which is their windowing environment. So you were just sitting out at a terminal. And then you had to go and compile drivers and all this stuff to get it working, which, really felt computer sciencey, right? You feel like you're really using your computers. And kind of the cool kid thing, there was a distribution of Linux. It might even still exist. I just haven't looked in a long time. There was a distribution of Linux called Gen 2 Linux. And its claim to fame was, the Linux kernel, that's the actual core operating system. We've talked about that, right? That's already out there and it's compiled, and then these different distributions of Linux. So we're going to call this, let's just do it like this.
The screen's froze.
Are you lying?
No, senor, it is frozen.
I wonder why that happens. How's it now?
Don't see anything.
Oh,
Just says that it's like loading.
okay. I'm on the wire. What happened?
Oh, mine's also just showing that it's started sharing screen, but it's blank.
Make sure. Yeah, I'm on the wired network. Let me try just sharing the keynote screen. Does it still just say starting to share?
Yeah.
Okay, well, that's not the screen I want to share anyways, then, so that didn't fix it. Let me try. Optimize for video clip.
It's working now.
All right, we're just going to roll with that. Okay, so we have these things called Linux distributions, and so anybody tell me some names of Linux distributions you've heard of? Raspbian, okay.
Kali Linux.
Okay, Kali Linux. What else? Ubuntu, okay. I don't think it's Ubuntu like that, right? Okay, so far you've stolen the one I took. we got any originals? So I'm guessing this was from Dr. Wall's class, Kali Linux. Raspbian was when you worked with Raspberry Pis, maybe 175, or I don't know, was I already doing that in your 200 class? I don't think so. Was I doing? Whatever. Yeah, and then Ubuntu I just mentioned, and then we also used it in the. Well, actually, we used Ubuntu in the 300 class. right? Yeah. All right, and I'm about to talk about Gentoo a little bit. Anybody, can we get at least one more on here just for historical purposes? Fedora, yep. So that actually used to be called Red Hat Linux. And then what they did is they split, kind of like Windows. They had a business and a consumer version. So Red Hat stayed as their server enterprise Linux, and Fedora, get it, the hat, Red Hat, Fedora, Fedora was their consumer product. So really Fedora was the one that had the better driver support. Then I'll throw a couple other ones here. Slackware, SUSE Linux. We'll leave it at that. There was plenty of Linux distributions out there. But the one I'm talking about here just for a few minutes is this one called Gentoo. And don't worry about the differences between these distributions for right now. The punchline is they all revolved. Create another slide here. Around the Linux kernel. Now the Linux kernel is an open source project that can be freely modified. But if you want changes to get incorporated into the core software, you have to contribute your code to the project and have it be accepted. So this is really a GitHub type situation where, you can fork the Linux source code and make changes to it and then recompile it. And now you have your own version of Linux, your own flavor of the Linux kernel that even if you just added a comment to one of the files, you can call that, Lipman Linux, whatever. But typically, if you're going to be working with the Linux kernel, you might be wanting to contribute to that larger project. And we'll probably actually try to do something at some point in the class where we'll maybe pick a little something and try to add a feature to the Linux kernel. And because a lot of times they have requests for contributions, and maybe we'll pick something that seems like it's maybe a 1 or 2 class period thing. I haven't looked in a while, so we'll have to see if there's anything that's even appropriate for that. And we'll actually put in a contribution and see if it gets accepted or whatever. But we'll pick something small just for the academic aspect of it. But in any case, you can certainly fork the code, download it, compile it, and write your own distribution around that kernel, or you can contribute to it. But generally speaking, when you install one of the popular Linux distributions, the kernel is pre-compiled for you so that installing does not take forever. All right, so what are the consequences of this? So this means, let's say 2 things. I might switch that to 3 depending on what I end up saying next, because I don't know yet. I gotta wait till I hear it. It's like what was the movie? Was it Old School, where they had the debate at the end, and Will Ferrell said he did this perfect debate, and he's like, "What happened? I blacked out." You didn't see Old School? Oh my gosh, Parker, you gotta watch Old School. Killing me. All right. So this means 2 things. Either all the driver support that the Linux kernel will ever have will already be included in the pre-compiled kernel provided by the installer, or there must be a way to add driver support after the fact. Now, even if we move away from Linux, which I'm sure is, which I'm assuming is going to be not completely foreign to all of you. Some of you maybe have used Linux before at some level, but certainly you're probably more comfortable with the Mac OS or Windows, most likely, right? So Linux is more of this other thing you've used. I would say not that many people run Linux as like their day in, day out operating system, unless they have that for like their computer programming stuff, and then their entertainment computer is something else. So I would say probably Linux is, unless you're a .NET developer, probably the best choice as a for geeks. At the very least, it makes you look cool. You know, it's like the equivalent of like a tattoo or something like that. It's like, what are you running home? You're running Windows 10? I run Linux. But I compiled my own kernel. That's where I'm going with this Gen 2 thing. I have my own distribution. I wasn't going to use that stuff, that prepackaged stuff. Like the people who make like homemade like dishes, and that's like supposed to be better, right? It's like, oh, this is like homemade lasagna, and it's like, it's not as good. Like, well, it can be if you're like a really talented cook or something, but it doesn't necessarily mean it's better. I mean, you might like go to, I mean, it was made in somebody's home. I mean, I'm sure somebody lives in that factory somewhere. Or like mice, there might be mice there. It's a home. But the punchline is it doesn't necessarily mean anything. All right, so there must be some way of adding driver supports. I was mentioning that like Windows, most of you are going to be more familiar with that. At some point in time, you've probably either gotten a new piece of hardware or hooked in a printer or something like that, where you had to install a driver. So clear, and you didn't have to sit there and recompile the NT kernel on Windows 7, right? Or Windows 10. It just, I ran a little software installer. It took 15 seconds and the printer worked. Okay, so somehow you were able to augment the operating system with this new fangled thing that taught it about this hardware that didn't exist when they first compiled that, right? So we can kind of make the assumption this is probably how they work today. But once upon a time, it didn't work that way. All right, so now they're called Linux kernel modules. That's what they're called now. We'll talk about that a little bit today, and then much more next week when we actually get in and start looking at writing a, like a fake driver for Linux that, so we don't have a piece of hardware, but we'll like pretend, right? That type of thing. But in any case, what was kind of cool about Gen 2 Linux, so really and even when Gen 2 Linux was out, kernel modules already existed. So there was never actually a reason to compile your own kernel other than bragging rights. Because like usually you sit down, you install Windows, you install Mac OS, you install Linux. It's like a 20-minute process, something like that. Maybe there's a little bit of hiccups when you have to like format the hard drive, you're creating multiple partitions. You get a little geeky with that, right? Okay. With Gen 2 Linux, you were installing the bootstrap for like, that's like the thing that from the computer's BIOS that hands off control to the actual operating system. So you compiled that first. So then you had kind of this intermediate operating system that was like barely running. They gave you a little control. And then you started, and it just gave you enough. It gave you the GCC compiler for C compiling, which we'll use quite a bit in here. And then what you did is you would download the Linux kernel source code. And you could go through, you would do a /configure, and you can go through and ask you, I don't know, I'll round down and say 50 million questions that you had to answer yes or no to for like whether you wanted this support to be compiled in and that support to be compiled in and stuff like that. And then you would finally compile. All right, now, most of us in here have had languages where we've compiled before, right? You've compiled Java. How long does a Java program take to compile? Your experience is instantaneous, right? C# in your software engineering class, instantaneous. You've done Android stuff, you've done iOS stuff, any of those things. You probably have not had an experience where something took drastically more than instant to compile, right? So we have two things at odds here. So first of all, when you're compiling all these files, You remember from the 300 class when you did C++ stuff and you have multiple header files and all that stuff. You can imagine that a kernel is maybe a little bit more complex than like our, one of our stupid little assignments, something like that. So probably more than like 3 or 4 C files, maybe more like 300 or 400, maybe even over 1,000. Then, probably now it's probably way over 1,000, but whatever it is. So but the idea is that not only were these files, were they multiple files, there was tons and tons of stuff in there because it was like complex operating system stuff. These system calls, we looked at the Hello World Linux thing last time, right? Or did I just mention it out loud? I think I looked at it last time. Yeah, so we mentioned that syswrite system call in Linux, which we don't have to know how it works yet. Well, we might look at, if I can get the source code, maybe we'll look at the Linux kernel and look at it, but we can probably use our imagination and come up with that syswrite.c is probably a pretty beefy program that does a whole lot of stuff that we're pretty happy we didn't have to write ourselves. And that's really nice that our nice C compiler will compile our Hello World program down to assembly code that leverages that other program that's also already compiled, so that we didn't have to write that as the compiler writer. You didn't have to output all that stuff. So you can imagine there's all these levels of complexity, even things that we view as being complex. Compilers, writing a compiler we view as being very complex. And the evidence is that it must be, because we don't have a lot of languages that come out that are compiled languages anymore, right? Interpreted languages are a dime a dozen. They come out every 5 minutes. The most recent compiled language that came out that meant anything was Swift. And before that, there hadn't been a compiled language since C# that meant anything, that was a popular language. I'm sure every year there's probably some startup company that's inventing the latest, greatest, whatever language that nobody ends up using. Okay, but so we can certainly assume that there must be a lot of complexity under the hood in that syswrite.c file that we're glad we didn't have to write. All right, so these are big programs. Now back then, so this is in, I'm guessing it's like 2000, somewhere between maybe 1999 and 2003. That was in the window when somewhere in there was Gentoo Linux when I was messing with it. So back then, you were probably running like Intel Pentium, possibly Intel Pentium 2 processors at like 233 megahertz, something like that. Maybe a little bit faster. Maybe you had a 600 megahertz processor, not gigahertz like we have today, but slower processors, much slower processors. So how long would you imagine that the Linux kernel would take to compile? Given the way I've kind of built this up, probably not instantaneously. Okay, how many of you think more than a minute? More than 10 minutes? Okay. I would say if you had a pretty fast computer back then, you're probably talking about something in the ballpark of maybe like 20 or 30 minutes to compile. But that's only if it compiles successfully. Because now you have hundreds and hundreds and hundreds of source code files, and you might get through the first bunch, maybe the first 400 of them error-free. Maybe you get a couple warnings here and there. Still got an executable, it's fine. Okay, so you've been sitting there, it's been compiling for 20 minutes, and then all of a sudden you finally hit an error. They're like, oh, well, what's wrong with this? You got to go back and you got to configure again. You got to re-answer the 300 million questions. Is that what I rounded down to 300 million or it's 300 million now? Okay, lots of questions. Okay, you have to re-answer those, figure out which thing you broke, right? Like, oh, I zigged when I should have zagged. I needed to answer no to that because since I answered yes to that, I couldn't answer yes to this. So I got to decide which of these two I want because those are not compatible with each other, something like that. Okay, then you got to go back and compile again. Now, the good thing is at that point in time, compilers had evolved enough where, it would pick up where you left off. Because any files that hadn't changed, that didn't have what's called a dirty bit associated with them, any files that didn't change would not recompile. You already had the output, so you can kind of pick up where you left off, and then you'd run into your next error, and your next error, and your next error. So finally, you see, you'd spend hours compiling this kernel. And then it's like, oh, it compiled. Well, how many of you have ever written a program in one of your classes that compiled, but it still didn't do what it was supposed to do? So syntactically, it was accurate. Logically, it was not, because you could still have conflicts between those yes and no answers you had. Right? So now you got an OS that doesn't work. All right. Now let's just say you debug that. So now you're probably on day 3, day 4 of the install. All right. I'm not exaggerating. I can't even tell you how many times you finally just give up on it and install Red Hat or something. It's on. You're good. You're all proud of yourself, like inside, you're like, I failed. I failed. So, in any case, so finally, let's say it boots. Now you're sitting at the the terminal, and because you don't have Windows yet, you don't have X Windows. You have to download that. You can compile that. So that's an application. That's a software application. It didn't come with it. So you got to go download your version of X Windows, and with the right theme and that kind of stuff. So there's there was KDE, there was GNOME. Now there's 4 zillion different ones. But then she had to compile that and run into the same errors again, blah, blah, blah. That one didn't take as long to compile. That was probably like a 1 or 2 minute type of compile situation. And then you add in the debugging and the warning. So now you're on day 6. All right. So you got a computer, it's technically running an operating system. You can use command line stuff that comes with the OS, but you have no windowing environment. Before long, you finally have a working version of Gen 2 Linux, let's say, with graphic user interface and all that, and you feel really proud to, like, you know what, this is better than one of those other guys because I didn't use a pre-compiled kernel. This kernel was compiled specifically for my exact hardware, not things that are compatible with my hardware that maybe won't take advantage of the latest, greatest, bells and whistle that's on my processor that came out 5 minutes ago, but it works on that classification of processor. Now mine works for this machine. It was like the only way you can get when the AMD 64 processors first came out, which were way ahead of the time. Intel had announced their Itanium line of processors that were kind of server class processors with their 64-bit processors, but they were very expensive and specific for like the server market. But then AMD, kind of in their push to try to compete with Intel, came out with their 64-bit processors. And it was called AMD 64. And they're supposed to be super awesome. 64 is better than 32 because it's a bigger number, right? All that stuff, whatever that means. Problem is none of the, like, if you were putting Windows, let's say on an AMD 64, it would support 32-bit architecture as well, but it had to do a conversion. So it was slower. So now you go out and you buy this more expensive 64-bit AMD processor that's actually acting like it's 15% slower than it actually is because you're actually running a 32-bit version of Windows on top of it that runs 32-bit versions of the software. Even if you install the 64-bit version of Windows, which technically would take advantage of your operating system, all the companies that make your software, like Internet Explorer, or Chrome wasn't around yet, but Netscape, for example, none of those were written for 64-bit yet. So then what you had to do is you had to have a 32-bit subsystem to allow you to run the 32-bit version of those applications on your 64-bit processor, making your 64-bit processor even slower. But now what's the cool kids doing over in Gen 2? Well, I compiled this OS for my 64-bit processor, so I'm native. Like, you want to run Netscape in 64-bit, no problem. Get the source code, compile it yourself. Find some bugs in there, fix them. Fix the bugs. Then you really feel like you're using your computer then. And then you go to print and you realize the print driver wasn't 64-bit and nothing works. And a lot of life lessons were learned in that process, but you know, you kind of get where I'm going with this, right? You know, this world existed and it still exists today to an extent. Somebody compiled the Linux kernel for Red Hat or Ubuntu, whatever, but they created it to be as general purpose as possible. But what happened is we moved into this world right here of something called a microkernel. Okay, the idea of a microkernel is keep the actual OS as tiny as possible. Where the actual OS does the most generic things. Nothing specialized or dependent on specific hardware. Then create subsystems that plug into the actual OS allowing for more flexible installations. The thing we're going to be looking at specifically is the driver modules. Okay, so modern day Linux supports this idea of OS modules, specifically for drivers is one of the module types, where you can think of the operating system as being your central point, and there are hooks. Almost the OS is like an API. Think of the OS like an API where it provides a collection of features that can be taken advantage of by external software, i.e. drivers, etc. We'll just say drivers for right now. Actually, in Linux, they treat everything, all hardware and everything is treated as a file. It's something part of the POSIX standard. We'll talk about that at some point. But so, you know, you can use that. When they write that driver, they're writing the driver. So drivers are written in terms of the system calls provided by the OS, provided by the kernel. Okay, so modern day operating systems operate off this idea of having a microkernel where you got that portion of the operating system that is pretty much hardware agnostic. It still had to target an architecture, right? So, you know, you're not going to have a single microkernel that'll run on Intel as well as RISC processors, as well as Spark processors. You'd have to recompile it for those different architectures, just like we've talked about. Compilers require two things: target architecture, target OS, right? When you're compiling an OS, you're not targeting the OS because you are the OS, all right? So if you're compiling an architecture, if you're compiling an operating system, what is the architecture? You could say, you know, maybe Intel or ARM, etc. So the architecture thing still exists. But then what is the OS we target with the compiler? Do we kind of have a chicken or the egg problem? If compiling code requires that I target an operating system and an architecture, and the thing that I'm compiling is an operating system, what operating system am I targeting? You get the question? So compiling in that previous slide requires two pieces of information. What architecture, maybe I'm modernly, maybe we're just compiling for Intel, a certain generation, let's just say i386 Intel. And what operating system, Linux, Windows, Mac OS, whatever it is. But if I'm compiling the Linux kernel, what is the OS I'm targeting? I'm telling you compiling requires those two things. What is the previous operating system? When you turn, if you just put a computer, how many of you built a computer before? You probably did in your 175 class. Okay, so in 175, when you built a computer, before you install Windows, you turn that computer on, what showed up on the screen? The BIOS. What do you think the OS in that stands for? Maybe operating system.
Basic input output system.
That's right. So this is a basic OS. Is your BIOS. So basic IO system. BIOS. So you have a very simplified but standardized BIOS. Think of it kind of like that VGA thing we talked about last class. That is the OS you're targeting. Super simplified, but at least it's a thing. Okay, so it's the motherboard manufacturer that had to provide that in order for them to be compatible. If the motherboard was created for Intel processors, it would use a specific kind of BIOS. Now they're kind of moving towards a newer EFI based BIOS, but it's like an upgrade OS. It's still an OS. Make sense? All right. Homework for next class, and I'll put it up on Blackboard right after we're done with class here. We'll keep it pretty simple. So write a 2-page paper discussing Linux kernel modules and how they work. And we're going to start looking at drivers, Linux kernel drivers, modules through drivers next week. Make sense? Questions, comments, concerns, bribes?
When's this due?
It's due next class, Monday.
Okay. And do we have to do the assessment for papers?
No, you don't have to do the assessment for papers.
Okay.
But you should mail a check. My address is up on a yeah, you said Bitcoin. Yeah, no, you don't have to do assessments for papers. All right, I will see everybody on Monday. Isn't that right? Is today Friday? Is it?
I found my exam. It's up now if you want to look at it.
Oh, you can follow me in my office so you can get ready for class.